welcome back. So I hope you have already figured it out whether this configuration will work in its own or not, and clearly this will not work. Why? Simply because this is not biased properly. I mean, for example, let's say your Vi is small signal. We haven't yet quantified what is small signal in case of a MOSFET, but let's assume Vi is very infinitesimally small input, right? Close to zero, right? So Vi is equal to some Vp sine omega t, where Vp, let's say, is 1 microvolt. I'm just taking a number, right? Okay. So what do you think is the status of the MOSFET? By status of the MOSFET, I mean, is the MOSFET on or is the MOSFET off? You might turn around and say, I haven't given you adequate information, right? So I can give you the information that you need. So let's assume the threshold voltage of the MOSFET. Let's assume threshold voltage of the MOSFET is 1 volt. Okay. So then what do you think is going to happen? So clearly the voltage between the gate and the source of the MOSFET is never crossing 1 volt, right? It's 1 microvolt sine omega t. It's never crossing 1 volt, which means your MOSFET is off, right? So clearly I'll have to apply a voltage between the gate and the source which is larger than the threshold voltage, at least larger than the threshold voltage, in order to ensure that I get the requisite operation out of the MOSFET, right? At least I can get the MOSFET to turn on. Note that I haven't yet turned my attention. We haven't yet turned our attention towards the output terminal. This is only what at the input terminal, right? But then, I mean, if our signal is of only 1 microvolt, so clearly this arrangement will not work, right? So what should we do, right? Another way of looking at this problem is as follows. So what is the ID VG characteristics of a MOSFET, or rather what is the current characteristics of a MOSFET, current voltage? So there are two characteristics of the MOSFET that we are familiar with. One is that between VGS and IDS, and the other is between VDS and IDS. So what does the IDS versus VGS curve look like? So clearly, till we have reached threshold voltage, the current is absolutely zero. Then what happens after that? The current starts to peak, right? But this is under what condition? When will this parabolic looking structure, parabolic looking profile be realized? This is only when under the condition that your VDS is greater than equal to VGS minus threshold voltage, right? Correct? Okay. So which means that in order to realize this, I'll have to ensure that there is a non-zero VDS that has been applied, right? Now let's turn our attention to the IDS versus VDS characteristics. What does it look like, right? For a fixed VGS, again for a fixed VDS, so it should look like something like this, right? Which means that, and what does this flat line symbolize? What does this flat line symbolize? This symbolizes saturation region of operation, which means we need to be on that flat line, right? I haven't drawn it perfectly flat. Let me redraw it. Okay. And what is this turning point? What is this point where the curve goes from looking like a linear parabolic to a flat line. This is that location of VGS minus threshold voltage. So you'll have to operate on this side of the plot. This is looking at the output terminal, right? Okay. So what does this mean then? Given that our threshold voltage is 1 volt, which means this is 1 volt, I have to ensure that the voltage between gate to source is at least 1 volt, right? And note that these are DC characteristics. This IDS versus VGS plot and IDS versus VDS plot, these are all DC characteristics, right? What do I mean by DC? All I mean is that, how did you get this plot? You got this plot by incrementally varying one parameter very slowly while keeping all the other voltages constant, right? The first plot you have got by varying the voltage between gate to source while keeping the drain to source voltage constant. The right hand side plot we have got by varying the voltage between drain to source while keeping the voltage between gate to source constant, right? Okay, great. So now what am I looking for? I am looking for an operation of VGS not only just greater than VTH, right? If VGS is just greater than VTH, we are probably here, right? But we would like to have a non-zero IDS, because ultimately we also want some GM, right? We also want some Y21. What is the GM or what is the Y21? Y21 is nothing but the slope of the IDS versus VGS characteristics, and clearly the slope is increasing as we go at higher VGS, right? So ultimately maybe we would want to operate somewhere over here, right? We would like to operate somewhere over here where I have certain VGSQ, where Q denotes quiescent point, and I will have a certain IDSQ where again IDSQ denotes the drain to source current, right? This takes into account, while fixing these currents and voltages, we are making a critical assumption, and the assumption that we are making is that the saturation condition is valid, right? That is, VDS is greater than VGS minus threshold voltage, right? And let's assume that again, now this is the input side, this is the transfer characteristics between the VGS and IDS. But if we turn our attention to the curve on the right, what should we look for? We should look for that particular value of VDS for which we get this IDSQ, right? So it might as well be, let's say this IDSQ is, let's assume that in this transfer characteristics we got IDSQ to be equal to 1 milliamps, right? Let's assume we got IDSQ equal to 1 milliamps for VGSQ equal to 2 volt. Let's assume that we have got that value, right? So how should I figure out what is the appropriate IDS VDS curve where we get this, which means that which essentially means that I'll have to plot multiple of these IDS VDS plots, right, and find out that particular plot for which IDS is equal to 1 milliamps. Let's assume that this plot refers to IDS of equal to 0.5 milliamps. Maximum IDS is 0.5 milliamps, which means I'll have to find another plot. And what will be that plot be? That plot will be corresponding to the maximum IDS of 1 milliamps, right? So which means that I'll have to find another plot where the maximum IDS will be 1 milliamps. And clearly, where will that break point be? Where will this turning point be? Will it be at the same point, or where at which the IDS of 0.5 milliamp plot break? Obviously not, because this will be a higher VGS value, right? Okay, so I will say that the minimum VDS, right? The minimum VDS for which I can satisfy both the input and the output condition is when I hit this value VDSQ min. If I can bias my circuit, if we can bias our circuit on this side of this region of this ID/VDS characteristics, right? If we can bias our circuit in such a way that VDS is above VDSQ mean, right? For VGSQ, which is equal to this VGSQ at which I have biased the transistor at the input side, then we would be able to bias our transistor in the right manner. Now, when I explain to you, if you are following this explanation, it seems very convoluted, right? It seems like I have to look at the input characteristics, I have to look at the output characteristics, and I have to figure out where exactly the VGSQ is, where exactly VDSQ min is, where exactly the IDS plot. I have to find out the IDS bias point at the input side, then I have to move to the next plot, find out the IDS characteristics at the output side. It looks too cumbersome a process, right? Our little human, at least my brain, cannot take into account so many information at once. So what we will do, we will simplify this process. We'll try and simplify this process and see, given that we can only handle one or two variables at a time efficiently, if we can distill down this information, down to one or two things that we should keep in mind, right? So what is the most critical thing we should keep in mind? The most critical thing we should keep in mind is the following, that your VGSQ, that is the quiescent bias point, this is the quiescent point, quiescent VGS, should be such that the transistor is on. Not only this, and also VGSQ should be such that the transistor is on and meets the requirement of GM or Y21. We can do this assuming, so do this exercise, do this assuming saturation, right? Why did I say do this assuming saturation? Because we will try to figure out whether the transistor is in saturation or not when we look at the output side. Let's not bother about whether the transistor actually is in saturation right now. Let's only concentrate on the input side, right? when we will go to the output side, we will try to figure out if the transistor is actually in saturation or not. If it's not, then we will take a call of what needs to be done, right? So okay, fine. So if that is the scenario, then what should we do? So we need to ensure that we get the value of GM. Now, from where will I get the value of GM? I haven't told you anything. Clearly, I haven't told you anything, but generally, a top level specification when you are building an amplifier is what is the amplification factor. So that will be given to you, right? If that is not given to you, for what reasons are you building an amplifier? So let's assume that you need an amplification, a gain of 10, right? Let's assume we need AV of mod AV of 10. Let's assume we are not bothered about the fact that AV is negative, right? Let's assume that we need a more gain of 10, which implies GM times RL is equal to 10. Now this is a multiplication of two variables which is leading to 10, which means that I can have infinite solutions of GM and RL, right? That is correct. But when you are building an amplifier, the other critical thing that will be given to you is the load resistance, right? Generally, the load resistance will be provided, right? So essentially, load resistance is an output spec. You are driving an RL, right? Since you are driving an RL, the value will be given. Again, let's assume that this RL is let's say 1 kilo, right? So let's assume RL is equal to 1 kilo. Okay. So what does it mean then? This implies my GM has to be equal to 10 by 1 kilo ohm, which is 10 millisiemens. Okay. So now in this particular configuration of amplifier, if GM is 10 millisiemens, what does it mean? What is the expression of GM? What is the basic expression of GM? It is mu n Cox W over L VGSQ minus threshold voltage, which is 10 millisiemens, right? Let's assume for the time being mu n Cox is given. Let's assume mu n Cox is 200 microamp per volt squared, or in terms of milliamps, let's say this is 0.2 milliamp per volt square, right? Let's assume this is given, right? This the technology that you are using ensures that this is the case, right? And for the time being, let's also assume that for some reason we have chosen W over L is equal to 10, right? So we can choose any W over L, right? We can choose any W over L. I can choose W over L equal to 1, 100, 1000, whatever I want. But let's assume we have chosen W over L. We'll come back later in the course and see what will happen if we change W over L. That is a critical design variable. But let's assume that we have chosen W over L for the time being, right? So we have to choose something, right? Let's start with W over L equal to 10. So what does this imply? This essentially implies that 0.2 milliamp times 10 times VGSQ minus 1 volt, where threshold voltage is 1 volt, is 10 milli, which means that VGSQ is equal to 5. This becomes 2, 5 plus 1, that is 6 volts. Okay. So this essentially implies that I'll have to apply a VGSQ of 1 volt. Correct? Okay, that's great, which essentially means that I have a MOSFET. I'll have to apply a VGSQ of 6 volts. What is VGS? How do I apply a fixed voltage of 6 volts? I'll have to use a battery, right? So let's say I have a battery. Let's say I have a battery between the drain and the gate and the source, and I say this VGSQ is equal to 6 volts, right? Now let's turn our attention to the load side, for the output side, right? So if VGSQ is equal to 6 volts and RL is how much? RL is 1 kilo ohm. So let's say this RL equal to 1 kilo ohm. Okay. So what do you think is the status of the transistor? Is the transistor on? Clearly the transistor is on because the VGSQ is greater than threshold voltage. So I have a channel. The inversion, since VGSQ is greater than the threshold voltage, I will be having the MOSFET will have free electrons in the channel to be held between the drain and the source junctions. But in order to do so, I'll have to apply a VDS, right? Is the transistor in saturation in the way I have drawn? What is the voltage difference between the drain and the source? The voltage difference between the drain and the source is clearly 0 because I don't have any battery between the drain and the source, or any potential between any battery at the output side. In this loop we do not have any. In this loop we do not have any battery. Since we do not have any battery, there cannot be any electric potential between the drain and or electric field between the drain and the source, which means there won't be any current, which means I need to put a battery, right? So where do you think I can put a battery? And not only that, we need to put a battery, we'll have to ensure that the battery should be such that the transistor is in saturation, right? So what is the condition for saturation? The condition for saturation is, for saturation, VDS has to be greater than equal to VGSQ minus threshold voltage. And since we have fixed VGSQ, which means VDSQ, let me say here VDSQ, because we are trying to fix the quiescent point here, should be greater than equal to 5 volt, right? Right? So this voltage difference has to be greater than 5 volt, greater than equal to 5 volt. So how can I ensure that this is greater than equal to 5 volt? So I can say that I put a battery. Where should I put a battery to ensure that this is greater than equal to 5 volt? I can as well, let's say, put a battery between the drain and the source and say this is VDSQ, and let me choose a value of more than 5 volt. Let me choose 6 volts, right? Let's say this is equal to VDSQ equal to 6 volt. This is greater than 5 volt, right? So do you think the transistor is in saturation? Clearly it is, because we are satisfying this condition of VDS to be greater than VGS minus VTH. And I mean, you don't even have to bother about the source. All you need to ensure is that check the voltage at the gate, check the voltage at the drain, and see if the difference is, if the gate is at least, or rather if the difference is less than or more than a threshold voltage, right? So the drain can go at least one threshold voltage below. If it is not going below one threshold voltage, then gate, you are good. So clearly this is in saturation. And what is the current? What is this current IDSQ. So IDSQ that will flow through the transistor is mu n 1 by 2 mu n Cox W over L VGSQ minus threshold voltage whole squared, which is half times 0.2 milli times 10 times this is 6 minus 1 5 25, right? 25. So this becomes 0.1 milli, this is 125 milliamps, right? So IDSQ is 25 milliamps. From where is this 25 milliamps coming from? This clearly this 25 milliamps is coming from the battery, right? So this will be the loop of the current that is flowing into the MOSFET from the battery. And clearly there will also be a current flowing through RL that is equivalent to 6 volt divided by 1 kilo ohms, that is 6 milliamps through the RL that comes from the battery. Okay, so far so good, right? Now we'll have to apply an input, right? So where should we apply an input? Note that, again, let me take you back a couple of slides or couple of pages. Note that incrementally we wanted the voltage between the voltage of the input Vi to appear between the gate and the source terminals. Correct? Okay. So then we said that if I directly apply Vi like this, it will not work. Why? Because transistor is not biased. Now my transistor is biased. How should I incrementally apply my input? Right? So clearly, I mean, if I have an input, source, R and RS, where should I connect this and how should I connect this? So let me ask you this. So if I sketch connect, RL should become drawn in a different color, right? Because this is an external thing that we were applying, that we were interested to get the amplification across. So if I connect my input, let's say like this, Vi, RS, this is 6 volt, this is 6 volt. Will this work? Clearly, this will not work. Why? Because the voltage across VGS is always 6 volt. So I have a battery of 6 volt connected directly between the gate and the source. So clearly, this arrangement will not work, right? So whatever incremental voltage that Vi will generate, all the current will flow out of this loop without causing any change of voltage between the gate and the source, right? So clearly this is not going to work. So what are the other options? If connecting this entire thing in parallel to the 6 volt battery doesn't work, what is the other option we can try? we can try putting it in series, right? So let's do that. So let's say we have this, and we put this entire, put our VIRS in series, and let's say this is 6-volt battery. Now ground is, we would like to ensure that the ground is common to everybody, so let's connect the grounds properly. Okay, so what do you think? Will this work? So what is the gate voltage now? So what is the current in the input loop? What is the current in this loop? This current in this loop is 0 because no current can flow in, right? Ig is equal to 0. So no current can be flown in. You are not drawing any current from the battery. If you are not drawing any current from the battery, what is this voltage? This voltage becomes Vi, right? Had you drawn current, voltage would have been Vi minus that current times Rs, but we have current is 0. So this voltage becomes Vi. If that voltage is Vi, what is the voltage at the gate? The voltage at the gate is Vi plus 6 volt, right? Right? So what is VGS now? What is the total VGS? Total VGS, right? Mind the notation, small v, capital subscript, which means total. Total VGS is Vi plus 6 volt, right? So let me write in terms of VGSQ, which is Vi plus 6 volts, right? So it looks like I have been able to apply an input, right? So what is the current? What is the total current that is flowing through the MOSFET, right? What is the total current? Again, note the notation, small I, capital DS, right? Which is half mu n C ox W over L Vi plus VGSQ minus threshold voltage whole squared, right? So which is equal to half mu n C ox W over L. Let me club VGSQ minus VTH together. So this becomes VGSQ minus threshold voltage whole squared plus other square term, that is half mu n C ox W over L Vi squared plus another term, that is twice into half into mu n C ox W over L, half and 2 goes off, so this becomes mu n C ox W over L Vi times VGSQ minus threshold voltage, right? Note that the total IDS is equal to, what is total? Total is incremental plus quiescent, correct? So that is small IDS plus quiescent, correct? And same old, what we'll do, we'll see that this quiescent cancels off. We get what remains. The remainder are the incremental IDS and 2 terms on the right hand side, right? And just like in case of Taylor series, if we assume that this term here is much less than, so let me make some space. If we assume that this term is much less than this term, that is, I can ignore the higher order terms in in a Taylor series expansion, right? This is nothing but a Taylor series expansion. If we can ignore the higher order terms, what do we end up with? We end up with IDS, that is the small signal incremental current, is equal to mu n C aux W over L. Let me write this VGSQ minus threshold voltage here times Vi. And what is this notation? This is nothing but GM, which means IDS is equal to GM times Vi, right? Which essentially means that this current that I have drawn here will be equal to, approximately be equal to IDSQ. And what is IDSQ? IDSQ is 25 milliamps. That is 25 milliamps plus GM times Vi. Correct? Okay. So as far as getting an incremental current out of my device is concerned, this job seems to be fine. But will we get, what is the voltage that we will get across RL? Note that the voltage that we will get across RL is still 6 volt because the battery has been connected in parallel with RL, right? So whatever do we do with the incremental current, all the incremental current will flow into the battery. Why? Because battery is an incremental short, right? What is the short circuit equivalent of a battery? Short circuit equivalent of a constant voltage source is a short circuit, right? So which means that the incremental current of GM times Vi will flow into the battery and not into RL. You would want all the incremental current to flow into RL, which is not happening in this model, right? So what is the solution? I would encourage you to come up with a solution of your own. Till then, till we meet in the next class, right? We'll see you in the next class.